Thank you very much.
Okay, thank you very much, Abos. I think we are 5 minutes before the time. Shirley, are you there? Yes. Nice to hear. I think you have to unmute the microphone.
Yeah.
Yes, nice.
Well, good morning. I mean, good evening.
Yes, good morning for you. So we will start a bit earlier if you don't mind. So, well, first of all, thank you so much for having accepted this invitation. So it's a great honor for us having you here on board of this webinar series. And well, the floor is yours. We are very much looking forward to your lecture.
Oh, thank you so much. I want to say the honor is all mine. Thanks very much for inviting me, Alejandro. I think early last week, some of you see me in the German SSB 4.0 event. So today, I think I prepared a presentation. Hopefully, there's new content that people still find, the excitement about the talk. So yeah, I will then, just give a very quick overview of this work. Can you see my screen?
Yes, perfect.
And this is full screen?
Yes, perfect.
Okay, thank you, Alejandro. So actually within my talk, I will talk about our joint collaborative work. We are very grateful that, I think it's already a couple years ago, before pandemic, Alejandro visited UC San Diego and gave a very inspiring talk on the use of machine learning AI in the processing of liquid-based batteries. And at that time, we have already been very intensively studying solid-state batteries. So in my talk, I hope that I will give a bit more material science perspectives on the manufacturing and the recycling of the solid-state batteries. Of course, machine learning is one of the very important tools in helping us to achieve these goals. So I think for this audience, perhaps it's necessary to mention a few things about the unique aspect of all solid-state batteries. I think the previous talk I learned quite a bit about the electrode processing for liquid-based electrolyte. So one of the perhaps the most important differences to realize is that the solid-state battery is not a simple replacement of liquid electrolyte with solid. In fact, the entire cell architecture has to change. And more importantly, in order to achieve the high energy density we have promised to the general public, we need to get away from intercalation chemistry. So graphite anode typically is not going to be used in our version of all solid-state battery. And for the cathode part, we have to find ways to improve the cathode loading. So for instance, the state-of-art liquid NMP-based electrode processing only have 4 milliamp hour per centimeter square loading. In our case, for solid-state batteries, we can go to 10 to 12 milliamp hour per centimeter square. So that's a very big change in terms of the electrode processing. And I also want to mention that the safety concern for the liquid-based electrolyte, large of it is coming from the flammability of the liquid electrolyte. So in the solid-state batteries, at least in the version that my group work on in UC San Diego, we do not put any drop of liquid inside the solid-state batteries in order to test the true safety aspect of the solid-state battery. So the promise for the solid-state batteries is, of course, multifold. Whether we can deliver these promises, I think the jury is still out there. We do not want to overpromise anything. However, based on the recent last 5 years of progress in the solid-state batteries, I'm cautiously optimistic that we will be able to deliver these goals. So, at our campus, my former PhD student, Darren Tan, who's now already back in Singapore, joined the A-Star to continue developing solid-state batteries. When he was a student, we did some single cell solid state battery demo, and those are just to kind of demonstrate the promising properties of solid state battery. One is the very wide operating temperature. The other one is the abuse tolerance for the bending, for the cutting of the solid state battery. So of course, there's challenges I will go through today, but I want to remind everyone that from materials to cell to pack to system, in each of these steps for solid state batteries, you can imagine for liquid, we need to have some very sophisticated method to do the temperature control. So I want to remind everyone that there is an opportunity here for solid state battery community to consider the pressure controls, to replace the very sophisticated cooling controls for the liquid-based cells. So moving forward, I would like to go through 4 major topics today. The first one is on the interface stability, and then on the scalability for the loading. That has a lot of content coming from our joint work with Alejandro's group. Then I will talk about the new anode strategy. Last but not least, I will talk about the recycling design. So all these work are either have submitted or they have been published. So for interface controls, I think perhaps the most critically important concept for the solid state battery is that one must consider this chemical versus electrochemical reaction. So let me dive deeper here. So in the liquid-based cells, the graphite anode and the NMC cathode are both chemically stable with the carbonate-based electrolyte. It's because the liquid we pick has a very high dielectric constant, and their HOMO and LUMO levels are actually outside the stability of the anode and the cathode. So when you have graphite and NMC, you can drop these powder into the liquid and wait there forever. There will be little or no reactions. And when we actually make the battery, of course, when we charge the battery, when we move the lithium out of MC to the graphite, of course, we make 2 very unstable compounds, right? And this is where the SEI and the CEI comes in. So the last, I would say the first 10 years of my academic career, I spent a lot of time trying to image and understand the SEI and the CEI. So when we look at the cathode, look at the solid electrolyte, the picture is completely different. There's a very important concept that the computational expert has already told us, that the electrolyte, solid electrolyte, regardless oxide sulfides, they have very narrow electrochemical window. So I will choose one that's the worst, which is the sulfides. So when you have sulfides, the first issue needs to take care is the chemical interface stabilities. For instance, the cathode NMC, when it's put next to the sulfides, the algidide sulfide is one of the model compounds we use, right? There is chemical reactions. So is lithium metal. Lithium metal and the algidide electrolyte also reacts. However, the difference here is the 2 things, the speed of the reaction and also the product of the reaction. So everybody knows that the graphite inside the carbonate electrolyte, when you form this SEI is very, very high quality. It's good to enable graphite to be stable in the charged condition, right? Because we have very little self-discharge in the lithium-ion batteries. It's only because this SEI is so stable. Now, think about here in the solid-state batteries, when we put 2 dissimilar solids together, the first thing you need to worry about is chemical reactions. Beyond that, when we sweep the voltage, then we need to think about electrochemical reactions. And these are 2 different things because the matter we deal with has very different lithium concentrations when we go to the as pristine versus charged samples. And in the solid-state electrolyte, you also need to worry about self-discharge. So the quality of the SEI is extremely important. We must worry about the quality of the SEI if we want to build a good battery. So on the cathode side, I think, perhaps the most influential work is coming many years ago from Toyota Research Group, where they showed this is our own data, but we can completely reproduce their data with the lithium niobate coating. The first thing lithium niobate coating do is to stabilize this chemical reaction here, because the NMC oxide and the aldehyde sulfides, they are chemically incompatible. Once you actually have a barrier layer there, the interface is greatly improved, and we can activate the NCA cathode reversibly for hundreds of cycles at room temperature. So if I use a cartoon to showcase what I mean here, is that on the surface of the cathode, this protective coating must be established if we put in oxide next to the sulfides. And this is also one of these challenges that in the manufacturing science we have to worry about. How do you ensure the perfect totally coverage in the cathode materials? And then when you go to the charged state, because at the charged state, not only your cathode is unstable, the problem is your electrolyte. Thermodynamically, the electrolyte would like to be oxidized, right? So we have conducted a controlled experiment to show that if you put carbon into aldehyde electrolyte, and you just make what we call this is basically a cell that made trying to understand the fundamentals of the oxidation stability of the solid electrolyte itself. So there is no other lithium source. The only lithium source is the lithium in the aldehyde electrolyte. And of course, lithium indium is used as the counter electrode to make this kind of cell. It's not real batteries, but this kind of controlled experiment enable us to study the true oxidation stability of the solid electrolyte, where you then see that the solid electrolyte is highly reversible. In fact, we believe in all the experimental data where people see, the reported capacities for the lithium sulfur based solid electrodes, the solid batteries, you always exceed the amount of theoretical capacity is because your solid electrolyte is participating in the electrochemical reaction. And this work, I think in Darren's one of the most important paper to show the electrochemical redox stability of the aldehyde electrolyte, very well explained this. So indeed, the aldehyde electrolyte is very challenging. However, once we understand fully what is the electrochemical reaction in the sulfide or aldehyde-based electrolyte, we need to know all the product, and then we need to think about, is there a way that we can actually mitigate these reduction and oxidation reactions, right? So I think, the whole reaction process, it's amazing how much electrons that the aldehyde, if you provided the pathway, okay, if you gave high surface area carbon to the electrolyte, you can actually see that the electrochemical window stability is precisely as the computational expert has predicted, very narrow. However, the good news for us is that the process seems to be reversible, and due to all the advanced computation and the characterization method, the product of the reduction and the oxidation are completely, in my opinion, the speciations are completely identified, even though some of them may be amorphous, some of them may be crystalline phases. There's still some debate about the distribution of the species. However, I think these results are highly reproducible, that we can identify almost all the species that has been predicted computationally. So in order to gain more confidence that from the electrochemistry and the computational data, we also turn into our collaborator for the solid state NMR. And by looking at quite a lot of the NMR spectroscopy, this is still ex situ experiment. We still haven't enabled the in situ experiment yet. We just want to confirm that the process is highly reversible, and it's actually the species that we have previously computational, like my colleague, Professor Xue owns early work to predict these products. We can more or less, quite confident about this. So the interface stability, interface understanding here is vital here because, the way how we enable lithium metal with algidide, the species lithium chloride and Li2S play a very, very major role here. They are indeed electronically much insulating and ionically conducting. So when we think about the SEI design, these products are very, very important for us to think about. Can we utilize lithium metal, or can we find another anode strategy? On the cathode side, the challenges, of course, once you have the sulfur on the cathode side, how can you deal with this kind of recurring product in the cathode materials? So the bottom line is in the solid state batteries, the interface phenomena is more complex. I mean, because we have a huge knowledge gap here about the interfacial product. So we actually had to obtain all these, for example, EIS, XPS, all the whole suite of characterization tools must be utilized to identify all the species in the SEI or in the CEI, and the consequences of these reduction or oxidation product is huge because, for instance, the cathode SEI or the anode SEI, they are very, very different. They are different in their electronic properties. They are different in their ionic properties. Well, the good news for us is really the EIS for the negative electrode side, the one that closer to the lithium metal, is pretty awesome in terms of its lithium ionic conductivity. The major challenge now our field is facing right now is for algidide electrolyte is that on the cathode side, it's because of the huge presence of the sulfur species, it becomes largely non-conductive for lithium metal. And this issue must be resolved. And I think that's one of the reasons a lot of the high voltage solid state electrolyte are still being studied. We don't have optimum solutions yet. However, I do want to emphasize that engineering-wise, there's some immediate solutions here. For instance, once we understand the kinetic pathway for the oxidation of the solid state electrolyte is provided by the presence of the carbon binders, carbon additives, we can actually change the very high surface area carbon black to the vapor growth carbon fiber. Right? Please don't call it nano carbon. It's not nano at all. These are very micron size, very cheap vapor growth carbon fibers. Once we change that, the surface area will be significantly reduced, of course, 3 or 4 times. But interestingly, by such, it's not a magnitude order difference, but by this reduction, there must be some other reasons there as well. We don't understand yet. We can actually see the decomposition rate at a certain charge density, charge rate is significantly reduced, and it can be clearly demonstrated in your charge profile. Because here, of course, I only add a small amount of the vapor growth carbon here to build the actual cell, right? So you can see that the use of the vapor growth carbon fiber can significantly reduce the speed of the solid electrolyte decomposition. But I think everybody agrees that for stabilizing high voltage, for example, NCM, we need to push it to higher voltage to activate the 200 milliamp hour per gram instead of 150, right? So the work is not done yet, but hopefully this work showcase how important it is to understand the interface stability in the cathode and anode materials. I'll come to the anode later. For the scalability of these solid electrolyte, as well as the stick loading cathode. Again, Darren's part of his PhD work clearly demonstrated this challenge. So just for this audience, I don't have to tell you that, in the laboratory scale solid-state batteries, we make this type of almost like a coin cells, right? The form factor is like a coin cell, but we need to monitor pressure. So we have active pressure monitoring. And with these screws, we can change the pressure, of course. But most of the lab scale, we call it a pellet cell. They are with very thick solid-state electrolyte. In the extreme case, it can be 1 millimeter thick. Of course, the ideal case, you should have 30 to 50 micrometer. So one of the things that Darren's work really, kind of demonstrated that the cell density, in order for the cell density to go to reasonably competitive with lithium ion, these kind of fundamental study must be translated to an engineering practice where we can utilize what's currently available for large-scale manufacturing. So we need to thin down the solid-state electrolyte. So this is the work that we have reviewed. We have already told the entire community, right? So why we choose these sulfide selections? Because that's the only one that the suppliers can give us 1 kilogram of solid electrolyte with reasonable price. When I say reasonable, it still costs $1,000. Okay, so we can try many different binders. We can try different solvent. So this is done before we actually came to know Alejandro's, the beauty of how we can utilize machine learning. But, I think a human brain is actually pretty powerful. So when we look at all the different binders, all the different solvents, it's very quickly that our students very quickly learned, okay, we need the kind of solvents that with only carbon and hydrogens, no fluorine, no nitrogen, because these binders and also non-polar solvent is preferred because we can then get very nice, solutions that allows us to process the solid electrolyte membranes. And I'll come to later, right? Because this is for selecting the speciation. So for actually make large scale 30 micron solid electrolyte, that's where we need to utilize the tools of machine learning. But here still, just to show what happened if you have those kind of polar solvent, polar binders, the PS4, P2S7, P2S6, this is the pristine solid electrolyte. If you use those polar solvent and the inappropriate binders, like the bondings of those sulfur-phosphate species will be totally altered, right? So the ideal case is that you use the xylene, which is completely retain the original sulfide aldehyde, sulfide speciations. So this is very, very important. We had multiple tools, both the XPS as well as the Raman, to show you that that's the case. You have to find compatible solvents to process the sulfide-based electrolyte. And of course, the conductivity measurement to understand what kind of hit you take if you use a liquid-based solvent to actually process these solid electrolyte. So we can see the performance degradation is quite clear. And, I don't have to go through the details. Everything is been published. So the next step is really trying to understand that, we can't really only make this coin cell based, right? Ideally, we want to make this really large scale row-to-row possible to make these 30 micron solid electrolyte, right? So the property of this solid electrolyte layer made in small scale is quite promising, 55 micrometer, close to 1 millisiemens per centimeter room temperature. Conductivity, we can test in the lithium symmetric cells. They shuffle the lithium foil with very little overpotential. So they all look good. Now, the workshop's theme is how can we scale up? right? So for this aspect, I think the best example here is to showcase our recent work with Alejandro's group. So it's quite clear that when we are making the solid-state electrolyte casting, there are these top priorities we need to achieve, right? So yes, uniformity, thickness, the ionic conductivity, probably the most important 3 criteria we need to have. But you know that the input is complicated, right? We have solid electrolyte has different microstructure. The liquid-solid ratio can be different. The binder type, the binder amount, the solvent, and sometimes we use co-solvent. So there are multiple parameters that we need to put in. Right? So we do need a large data set, but you know the most important thing is thanks to the collaborative work, we have no problem collecting the data. But you know, the data, of course, has many different dimensions because we are changing the polymer content, we are changing the solid liquid ratio, we are changing the binder amount. So when we collect these data sets, we're very fortunate to have the collaborator coming from France to teach us how to do the principal component analysis to determine the correlations. And I even learned that, okay, you know, my lab efficiencies and the, you know, happiness levels are kind of, you know, orthogonal with each other. That's a joke my students have played with me. But, you know, I actually thought that it's a very good way to showcase the importance of principal component analysis. And then, of course, we need to classify the samples into different clusters. And I would say that perhaps, you know, the separating of the clusters within the boundaries, I think this practice really taught the experimental people a lot, that many of the input-output parameters, it's very difficult to use human intuitions to find the correlation or anti-correlation. And then we also taught the computational people, the machine learning people, that our domain knowledge, the importance of material science knowledge, help to label these, classify these clusters in a very, very accurate way. So these are really truly two-dimensional, dual dimension, you know, collaboration, because we taught each other really, really important things when we try to implement machine learning into the optimization of the large area solid-state electrolytes. So, you know, of course, the final outcome is that we determined a very promising set of parameters where those will enable the experimental people like us. So Yuting Chen took over the work from Darren. Yuting is currently my PhD student, and he can now reproducibly make very high uniformity, high conductivity, large area films because of this exercise we went through with the machine learning expert. So I would say that based on our own experience, I think you know, we really quite well benefited from the machine learning community. The other area we haven't started collaborating yet, but I will put out here today. Early today, I mentioned about the high area loading material, high area loading cathode materials. So this is probably the first time we're reviewing these videos that for the high loading cathode, we can go way more than 6 milliamp hour through a dry process where you can actually see it's a standalone cathode material that you can bond it to the current collector later. But, you know, the solution process will not get us there. This process is completely dry, and we're using a special type of PTFE-based binder. And there's, of course, lot more processing, lot more optimization to be done. But what we cannot do with NMP-based liquid-based material, liquid-based processing method, we can achieve with the solid-based processing method. Okay, so yeah, the reason that you cannot do it with the liquid, I think Darren put this picture here is like a making the pizza dough, and I think for folks who are really real foodies, you understand that the recipe and the procedures are extremely important. So I'll leave this as it is here. So in my opinion, this is another area that machine learning community can help a lot to help optimize the process and go for very, very large area row-to-row processable dry electrodes. So once we make these dry electrodes, the characterization become another challenge, because for thin electrodes, you can do the cross-section, you can use focused ion beam, but for the thick electrodes, so we have a collaborative effort with Thermo Fisher Scientific to try to utilize X-ray CT to do the tomography and to help us to examine the homogeneity and the uniform thickness of the films, right? So here is the reconstruction. You can see beautiful dry films, like the films made from the dry electrodes has better distribution of the binders and better, retain the secondary particles, morphologies, and in the liquid case, because of the solvent evaporation issues and the gravity, right? Because the bigger particles try to settle down while you're waiting for the solvent to dry. So really big problems. So again, Jonathan, who has already graduated, he really specialized in the CT from micro to nano, and then correlate these with the SEM and the TEM to build an extremely holistic, and I would say multi-scale models where when we think about the battery modeling, right, these data needs to be collected. So using machine learning to propagate information gained from micro CT, nano CT, all the way to FIB and TEM is extremely helpful. And I would say all the information collected here, not just useful for experimentalists like me, but for people who build a complete modeling of the full batteries. We're crossing like nanometer to meter scale. These machine learning will, no doubt, it will become indispensable tool for the future of the battery research. So we have put together a perspective article really to stress this important tool. So just a couple more words about the dry electrode process. I think at the moment in our laboratory, we can make 240 micrometer thick dry electrodes with very good current density. I mean, we are utilizing, we are academic research lab, right? So we can actually enable 10 milliamp per centimeter square. Of course, the utilizable capacity drop quite a lot, but these current densities at room temp at the 60 degrees Celsius is encouraging. Again, I emphasize there's still a lot of room to be improved, but it's exciting for us to realize that a high area capacity with dry electrode process is totally doable. So once we we push the cathode side a little bit more, let's now look back on the anode. So I mentioned in the beginning of my talk, lithium metal is a must. Okay, we have to do that if we want to deliver 500 watt-hour per kilogram. We don't have other choice. And lithium metal has many problems, right? So critical current density at room temperature is so low. Even if you go higher temperature, yes, you can push up the critical current density. However, this is a CT tomography. And I think Jean-Marie is going to join SAFT very soon. But you can see that the early work he has done in my group really changed our view of what lithium metal's response is to the stack pressure. So everybody knows during the synthesis of solid-state battery, we have to put a large pressure because we need to establish contact because the solid cannot flow. So the only way you reduce the impedance is actually to put a very high stack pressure. during the cycling, during the electrochemical cycling of the solid-state battery, if you use lithium metal, you cannot stay in that high pressure because the yield strength of the lithium is actually pretty low. So when we do very high pressure cycling, this is all the CT, you can see immediate shorting of your batteries. And even if 25 megapascal is too high, and it really encourages the lithium migration and creeping. So with the less than 5 megapascal, lithium metal can be cycled at room temperature at very low critical current density. So indeed, if you go to higher critical current density, the cell will still short. Okay, so this is one of the major dilemma that we are facing. Like we have to at the moment, before very creative method coming out. So we have some ideas how we can enable pure lithium metal. However, at the current stage, we must find an alternative anode strategy because of the challenge of the lithium metal cells. I do want to say the good news is don't worry about the cell shorting. Okay, no fire, no explosion, very safe. It just shorts. It just make the cell fail. It doesn't cause any damage in my glow box. But let's talk about the alternative anode. Sorry, because I think the excitement of silicon in the liquid electrolyte last about a decade, and in recent years, people really start to get frustrated with the enabling of the high loading silicon anode in the lithium ion batteries, right? So we, obviously there's many reasons why silicon should be chosen. Once again, I was, the thing when we did the literature review of how much work has been done in our field with micron silicon, nano silicon, sputtered thin film silicon, the rich amount of literature taught us very important things, right? So you can call it a way of human learning. It's not machine learning, but I think machine learning, like looking at the data set in the literature, like earlier, I think the previous invited speakers have talked about. I think the great thing here is that you can see majority of these silicon materials is actually in the very low areal capacity loading, but in the sputtered silicon film, there are examples where you can do 100% silicon loading, but very low areal capacity, right? So the maximum is probably like 2.5, and they all have shown pretty limited cycling data. The only cycling data we have over 400, these are all full cell cycling data, right? The open circle is that there's a pre-lithiation strategy. So in summary, when we look at this few thousands of papers in the last decade, right? These are all liquid electrolyte silicon, right? So the big question is what different things solid state battery offer to our silicon research community that is totally different from liquid, right? So fundamentally, this question is really important. So one of the, I would say the secret source for doing the battery research is that we have to do the research not for making the best batteries. We really should do the research because it's scientifically so interesting and so stimulating. So I gave Darren this very simple question that what aspect of the solid electrolyte can offer that is completely different from liquid. So the first thing come to his mind is really the liquid can flow. The solid cannot flow, right? So when we do liquid, it's continuous formation of the SEI, and there's trapped lithium in the lithium silicates, lithium silicon alloys, because they got detached from the electronic pathway. Now we have a solid, right? So if there is crack happening, what's the big deal? The solid state electrolyte cannot flow. I want everyone to remember this, right? And when we form the SEI, if I do form a interface, because I'm not putting any solid electrolyte into the silicon, right? So if the interface formed here, there's no way it will flow down because they're solid. Now, the second thing is the lithium silicon, because lithium silicon has so high lithium conductivities. The only thing I need to worry is the electronic conductivity. So we debate a long time whether we need to put carbon into the silicon anode. And the answer is absolutely no. If you look at the electronic conductivity of the bulk micron silicon, they should be good. They should be very good as the anode materials without adding any carbon. So the outcome is this, if you do put a carbon, I will tell you the stability issue, right? Remember the reduction potential. So you put a carbon in, it will accelerate the reduction that you will have Li2S for. So get rid of the carbon. I mean, the whole series of the spectroscopic study is to show do not put carbon in the silicon anode in the solid state. So I think, the SEI growth is completely quantified in our work. I think in our archive paper, we introduced the method clearly. We want to show that only the first cycle you will form SEI, subsequent cycles, the efficiency just after one cycle very quickly ramp up to above 99%. This definitely, showed us that, I also mentioned about the high temperature stabilities. So when we have a solid interface, we showed you previously solid should have very large operating window. The use of the silicon obviously showcase the same thing, because the solid, if you have a higher if you have a stable interface, the raising of the temperature only improve the transport properties because the interface is stable. So there's no side reaction to be promoted. So the cell actually stays very stable at 55 degrees Celsius. And if you think about this advantage of the silicon-based solid-state batteries, it is truly, truly exciting. All right, so morphological wise, I don't have time to go through today. I just tell you the chemomechanical properties of the silicon is still an intense research topic. I don't have time to go through today, but you can already see the huge change before and after. So there's still a lot of work to be done there. And we were able to enable 12 milliamp hour per centimeter square loading, which is perhaps one of the highest loading that you can find in the literature. So I do encourage all of you, if you have time, to go through the archive, the paper that we have already put out there. The last topic I would just say, just 2 slides on the recycling design. Because I think I can skip this. Everybody knows lithium-ion batteries are very difficult to recycle. They need to be recycled, but they will be more costly to recycle. That's one of the joke that I heard, like some of us wish that there's gold in the current collector so that we can have a good reason to recycle the graphite anode. But, let's all remember that we are in the this bad situation about the plastics because of we didn't recycle. So, we cannot just recycle for profit, that there are other reasons we have to do recycling. So for solid-state batteries, I would say my colleague Zhen Chen, who's a co-supervisor for Darren, very early already start to consider the recycling because, we were saying lithium-ion battery is a class 9 hazardous material. So you can look at the shipping cost. If anybody who have shipped the lithium-ion batteries, you know how expensive it is, right? So for the solid-state batteries, we do have the advantage of designing recycling into the production cycle. So this is, I would say, one of these directions that Professor Chen's group is pursuing, and we definitely have done both the energy consumption analysis and the greenhouse emission analysis that looks very promising with the solid-state batteries, we do this direct method for separation of cathode and solid electrolytes, and it does look very promising from the recycling perspective, and it also will be considered as, we regenerate the materials can be directly used for battery. So in this solid state electrolyte example, I'll show you that with the thermal annealing, with the mechanical milling, there's multiple ways you can recycle and regenerate those solid electrolyte and recover its ionic conductivity. I think, since my time is coming up to the end, I will not talk too much about the recycling, but I just want to say that, the pristine cell and the recycled batteries made the cell, the performance is indifferent. They are really, really similar. So this shows us a good future directions where we should think about the solid-state battery as an opportunity for our field to build recycling in the manufacturing process. So yeah, that comes to the end of my talk. I just say that I discussed this 4 different aspects, and hopefully, it does connect with the machine learning community and to think about all the interesting problems that we will be able to work on together in the coming years. Yeah, the remaining challenge is quite clear: precursor, processability, pressure control. So I think, as my time is coming to the end, I should stop talking and, give a chance for answering questions.
Thank you very much, Shirley. Amazing presentation. Thank you very much. Very, very inspirational as usual. Thank you. So I think there are plenty of questions.
Yeah, we have many questions. Yeah.
So Fernando, maybe you can go ahead. Yeah.
Yes, Shirley. So here, Andrew Borkers asks, how is the metallic lithium usually applied to the SE layer? Is it reasonable to heat the coated lithium layer above melting temperature afterwards to melt it into the rough surface structure of the SE layer?
Very good question. Yeah, so we remember that we can use both temperature or pressure as the method. At the moment in my laboratory, unfortunately, we only have this pressure method, which, in my opinion, is very crude and very poorly controlled. Yeah, so I would encourage people who have special heat treatment method for putting lithium layer next to the electrolyte. It should be definitely explored because lithium metal has so low melting temperature that we can utilize its good properties to do that.
Thank you.
I haven't done it, but I think it's a very promising direction.
So also we have here Mustafa Mohammadi asking, do you have any measurements for cycling performance, capacity per number of cycles? What is your plan for the formation of lithium dendrites in the anode part?
Yeah, so for the lithium metal anode, at the critical current density 0.3 milliamp per centimeter square, we can cycle a few hundred cycles without problem. The cathode capacity is close to 180 milliamp hour per gram. So unfortunately, you cannot ramp up the critical current density unless you ramp up the temperature at the same time. That's the current status of the lithium metals. Now, on the silicon anode, at the moment, we can do 5 milliamp per centimeter square at room temperature, and the capacity per, the utilization of the cathode is over 160 milliamp hour per gram, and the thickness is 10 milliamp per centimeter square. So very thick cathode loading. So I agree with what last week Solid Power's CTO said. The first generation of the solid state batteries probably is going to be silicon based. Of course, I think that the optimization for micron silicon versus nanosilicon still a long story. I think we don't have enough data to conclude yet. But for lithium dendrite, if you do critical current density above that critical current density, you will have dendrite. And the most striking part is that when the dendrite goes through the solid electrolyte, we don't even know they are metallic lithium or they're just forming, product of the reaction with lithium with the solid electrolyte. So it is a very, very complex chemical, mechanical, and electrochemical coupled effect. So at the moment, I don't think anybody understands in the solid state electrolyte how dendrite is formed.
Okay, we're going to hear fast track question that has been very voted by Arnaud Dubaret, who asks, could you please give some more insights to the dry processing of solid state cathodes? What mixing technology would you recommend to obtain homogeneous composites?
Yeah. So this one, of course, contains a lot of intellectual properties. Yeah. So I think many of you maybe know that there's a San Diego company called Maxwell was specializing in the dry electrode process, and I have had the pleasure working with them since 2016. And later they became Tesla San Diego. So I have to apologize that I cannot give too much of the detailed information. However, what's out there in the public already give us a lot of good hint. So number one is the binder cannot be cannot be PVDF based. It has to be PTFE based. And then also the dry processing also allows the binder amount to be very low. And so the mixing technology, I think pizza dough is what my lab is using. You saw the pizza dough with the handmade pizza dough. And I think the PhD student and the postdocs, we can definitely use the handmade process. But for the companies and for the national labs, I think it's time for us to seriously think about the highly automated and other ways of roll-to-roll process, how you can make dry process. But the dilemma is always that we already built up a lot of battery processing with wet process. So how can dry process gain momentum is still a question for me. Because we already have a lot of capacity for wet process.
Yeah, even so the fundamentals of the extrusion process. I mean, there are no models to describe that. It's very in terms of physics models.
Yeah, that's why I'm very happy to be here. I'm actually asking help for the machine learning community to work.
I raise my hand so I can help because it's very fascinating topic. Yeah.
So here we have another question from Alexis Laforge, who starts thanking you, Shirley, for this great talk. And then here it says, I wonder if the change of mind of Solid Power towards silicon anodes was due to a collaboration with you, or did they come to the same conclusion by themselves?
Very good question. I think the great minds think alike should be the best answer. I do want to take also this opportunity, Solid Power comes from University of Colorado Boulder. And one of their founders, Professor SSE Lee, actually he's a student back in 2016, became my postdoc, Dr. Tom Yusek. So in some way, we are genetically connected because, Tom Yusek helped me to build my solid state group. So I do think that, once we understand how things work, we tend to think the same way. I think the only difference is that we are academic institutions, so we can do what we call the crazy things, like totally take out carbon. So I'm very happy that we took this, crazy action because, for company, maybe it doesn't make sense to try some of the crazy ideas, but I think the university students and the postdocs should be always encouraged to try things differently. And I think that in this case, it really well paid off. Thanks for the question, though.
Here we have another question by Jens Anhalt, who asks, for calendaring a composite cathode in an SSB, would there be an optimal porosity like with liquid electrolytes, or is a lower porosity towards zero always better, meaning improving contact for both electric and ionic contacts?
Yeah, so this is a very good question. I believe, so in our chemical review paper, we clearly put a void as a negative contribution to solid state for the cathode composites. In fact, this is in my opinion, so you can see in our archive paper, the decay is still happening. So I believe it's because the void generation in the cathode. At the moment, we don't have clear evidence. However, we do know that the NMC cathode we use, when we take lithium out, the volume is shrinking, right? So one should, I think a lot of you understand the lithium cobalt oxide, when you take lithium out, the volume is expanding, but nickel-based materials is different. The volume will shrink. So when it's shrinking, I don't know when it's shrinking, even though we have the pressure on, but it is because it's a composite electrode. So I don't know if it created a void between the cathode or the solid electrolyte. So yeah, it's definitely a huge challenge, and this is one of the reasons the stack pressure control is still very, very important. So yeah, I think that the future design for the composite cathode, one really have to think about how to avoid porosity. I don't think porosity is welcomed in the intercalation materials and the solid state battery. It is welcomed in the silicon or lithium because they do have large volume change. So you have to think about how to design porosity for better cycling. But for the NMC cathode, I don't like porosity at all.
So here we have another question from Teo Lombardo here from the artistic crew. He asks, the prospects of using silicon in ASSB is very exciting. And it is true that the continuum formation of SEI, most likely, is not a major issue. But what about the lots of particle contact for SE expansion?
Yeah, loose. I think what he means is loose of particle contact.
Yeah.
I hope you're not one of our reviewers. So it sounds exactly like the question. Yeah. So very, very good question. So unfortunately, I don't have time today to go through the mechanical behavior of the lithiated silicon. So the first cycle for the silicon, it should be considered as a formation cycle. So because the microstructure of the silicon changed dramatically, okay? So the loss of particle contact is possible if you don't adjust. Because the first formations, think about in lithium-ion batteries, you have to degas after the first formation cycle, okay? So I'll leave it as here. So you do have to think about smart engineering design to avoid that, but it is a totally engineering problem. It's not a science limitation.
Mm-hmm.
Yeah.
And maybe a follow-up in this question also, can you share your view about anode-free ASSB? Do you think that this would face similar challenges respect what you showed for the case of lithium metal anodes? So the difficulty or the impossibility to work at high pressure, for instance.
Yeah, so I hope my talk made it quite clear that we are not giving up on lithium metal yet. We just don't have good strategies yet. So I would say anode-free is one of those strategies that are currently being explored. So I think in the solid state SSB 4.0 last week, I showed some pictures about the huge volume change due to the anode-free architecture. So at the moment, I think not enough mechanical people knows mechanical engineering are helping the battery field. So I think unless somebody figure out how to deal with the pressure change. So if you have anode-free, right? So each time 10 milliamp hour per centimeter square means you're moving 50 micron of lithium. So if it's 10 layers, that's 0.5 millimeter, 500 micron. So I don't have any strategies can deal with this kind of pressure change due to the large volume change. But I think my postdoc did this submarine, right? He said make the battery under 250 meter water. So it's totally isostatic pressure. Of course, it's not practical, but I wanted to say that anode-free cannot be realized unless somebody with a very, very smart idea on mechanical designs. And we can then explore this possibility. I think it will be more challenging than lithium metal anode. But I think that's the part of things about academic research. We are curiosity driven. We're not profit driven. So it's very nice that, one of my students is actually working on that. And I think many people in the audience probably will choose this topic to explore as well.
Yeah, sure.
Fantastic. Well, maybe a last question before calling it a day. So here, Shirley, do you think that lithium metal, which has low contact area, will be the final solution? Or a more sophisticated 3D anode material will replace the lithium for increasing the current density? And a question of mine, what happens if AB using ASSB crashes in a rainy day?
Okay. Very good questions. Yeah. So the first one, I think for the solid state batteries, I think that contact area has to be sophisticated. So it's going to be 3D, I think, because the solid electrolyte itself is, has a complex microstructure. So if you want to intimate, support at the interface, it's going to be 3D. I think regardless whether we want it or not. You can start with a flat piece of lithium metal. After the electrochemical reaction, it's going to become 3D. So I think that and the current density, critical current density, in my opinion, cannot go up unless we go 3D. So we don't have choice, this one. Okay, the second question is extremely insightful. I think it's a good question, whether if the sulfide-based electrolyte, we have a rainy day. I hope it's a pouring rain. It's a very, very heavy rain, because that will reduce the hazardous level by a lot, because you dilute the, and remember the solubility of H2S in water is actually very, very high. So when we have H2S, we would rather it to be in the liquid form instead of in the gaseous form, because if you smell it by the gas, it's actually more detrimental, right? So because the liquid case actually is, so in terms of toxicity and the safety aspect for the algae-dyed electrolyte, I think very soon that people will release those kind of studies, because I think the H2S is being overemphasized. I want to say that Li2S is a very strong bond. To form H2S bond, there are certain conditions that has to happen, and I think that hopefully that the large amount of water is actually a good thing. But I think our major issue right now is actually in terms of dry room compatibility and how do you process it in the dry room. That will directly relate to your safety concern questions later. So we hope in the later this year or early 2022, we will release those studies to showcase the dry room compatibility and the safety aspect for people who work in this kind of dry room. I think this is an excellent question. Thanks for this very humorous question.
Thank you very much. Thank you very much, Shirley, for very, very nice discussions. I think we had a great presentation from you and from Sam as well. Thank you very much for being on board.